Okay, so we're gonna talk today about the SP lock, and we're gonna take a look at how it works, why it works, and what is the main application that we can have from this lock. So here we can see that there are four main uses for this lock. But before we look at these uses, which are the indication of shallowness, correlation, determination of water resistivity, and detection of permeable beds. Before we go deep into this, well, not deep, actually, I'm gonna just cover these things superficially because these things are complicated, but it's an introduction to the SP lock, basically. And I'm a junior prison physicist. I'm still learning about these things, and so if you have any correction to make or any clarification, I would really highly appreciate that. So the SP lock, see, take a look at different websites. So this is a nice graph. So the spontaneous potential lock measures natural electrical potentials that occur in boreholes and generally distinguishes porous permeable sandstone from intervening shells. The natural battery is caused when the use of drilling mud with a different salinity from the formation waters causes two solutions to be in contact that have different ion concentrations. Ions diffuse from the more concentrated solution, typically formation water, to the more dilute. The ion flow constitutes electrical current, which generates a small natural potential measured by the SP tool in millivolts. So when the salinities of mud filtrate and formation water are the same, the potential is zero, and the SP lock should be a featureless line. With a fresher mud filtrate, and so more saline formation water as sandstone, we show deflection in a negative potential direction to the left from a shale baseline. The amount of deflection is controlled by the salinity contrast between the mud filtrate and the formation water. Clean, shale-free sandstone units with the same water salinity should show a common value, the sand line. In practice, there will be drift with depth because of the changes in salinity of formation waters. The displacement on the log between the shale and the sand lines is the static self-potential SSP. And from this SSP, you can actually calculate water resistivity, an equivalent water resistivity and water resistivity, because there are some plots, for example, that use this static SP as SP. And from this SSP, you can calculate the resistivity of water. Okay, okay, so we know what's going on here. So there's some currents, some potentials generated between those fluids that get into contact with different concentrations. Okay. So these potentials give us an idea of the rock, right? Because if the rock is porous and permeable, there's going to be more flow, and if we have a shale, it's going to be impermeable. There's going to be less deflection. Let's see more information about this lock. So we have a recording voltmeter, we have a ground electrode, and an SP electrode. So the SP electrode is the one that is moving up the borehole, and is measuring the natural, spontaneous, or spontaneous potential differences that exist between the borehole and the surface in the absence of any artificially applied current. So you have an electrode, usually lead, is lowered down the wall, and an electrical potential is registered at different points in the hole with respect to the surface electrode. In order to record a potential, the hole must contain conductive mud, as it cannot be recorded in air or oil-based mud. So we need to have a conductive mud to run this operation. So the logging rate is approximately 1,500 meters per hour, and recordings are continuous. So, are the causes of the spontaneous potential? We have two causes. We have the electrokinetic potential and we have the electrochemical potential. The electrokinetic potential relates to movement of fluids, movement. So if we have the depletion or if we have different differential pressures, we are going to have more fluids invading or more fluids coming down, coming from the formation to the well, or if there is movement of fluids involved, that's when electrokinetic potential enters the picture. But if what we have is just ions moving and diffusing and creating these small currents, that's more like electrochemical potential, right? So in the electrokinetic potential, we have the mud cave potential and the shell wall potential. And in the electrochemical potential, we have the liquid junction and the membrane potential. So, for example, here we see that the electrochemical potential is the sum of the liquid junction and membrane potential. So we have the mud in the borehole that we already said that it should be conductive, and then we have our shale and our let's say porous media or sandstone. So there are two potentials that are being created here. We have one potential that is being created between the fluids of the virgin zone and the embedded zone, and we have also another potential created in the membrane between the virgin zone and the shale. So if we sum up all these two chemical interactions of ions, we have to remember that ions move from the highest concentration to the lowest concentration, and by doing this movement, they create currents and potential. So if we sum up all these two contributions, we're going to get the final electrochemical potential contribution to the SP curve, right? And this is the electrochemical potential. We have the diffusion potential. So again, if we have two solutions, two fluids, one is weak solution, one is concentrated solution, then the ions that are in the concentrated solution will move to balance salinities, right? So, but some ions are faster. Chlorides are faster than sodiums, right? So, but when they move from right to left, they create a net current flow from left to right, and that's what generates the the potential. So here we have shell potential, original conditions. We have the cone water in sandstone, in the sand. We have our shell here, the mud, and you have dynamic conditions. You have ions moving from the shell to the shell, and from the shell interacting with the mud. That's electrochemical. And if we take a look at electrokinetic potential, it's movement of charged ion through mud cave into permeable formation and flow of fluid from borehole into shell formations. So these are low in the sense that we don't see a lot of movement into shell because these are highly impermeable rocks. But there can be some movement of charged ions through the mud cave into permeable formation. That would be more feasible. So how it works? The spontaneous potential produced in borehole are actual result of these two processes combined. The mud filtrate is less saline than the formation water. so it becomes negatively charged as a result of diffusion potential. But above the sand, opposite the shell, because the shell potential is the saline solution, one filter becomes positively charged. The excess charge is therefore negative opposite the sand and positive opposite the shell. This couple works in a complementary sense and creates SP current flowing between the mud filtrate, the porous formation, and shell. Okay, so, and also, this is when it gets complicated, like the fluid makes all these things complicated, because if you have fresh water, then your deflection is going to be, let's say, to the right for sandstone. But if what you have is brine, then your deflection is going to go to the left or something like that, right? And your shell, we have less deflection. So, for example, in this case, we can see that we're having our baseline for shell here when there's no deflection, or deflection to the right, depending on how you want to look at it. But our baseline for sand is this line to the left. The difference between those two lines is the static, or SSP. So how do we read this log? We have here 3 types of sandstone. So let's focus first on the first one, which is this one. And here we have, in sand A, we have the deflection of the SP curve to the left. Okay, so it's indicating permeability, it's indicating that we have a change in lithology. So we know it can be a sandstone, or it can be, there's a change in lithology for sure. But because the deflection is to the left, we know that the formation water is saltier than the mud filtrate. Okay. But if we take a look now to sandstone number B, the deflection, as you can see, is less than in sandstone A. So here we are decreasing the salinity in comparison to the sandstone A. So we have less salinity, fresher formation water. So less deflection. But if we take a look at the sandstone C, is reverse. So now the deflection is to the right. So again, the deflection indicates the sandstone is indicating a permeability there, but the switch to the right comes from the salinity again. So we know here in this case that the water that we have in the formation is fresher than the mud filtrate. Okay, so the water resistivity is greater than the mud filtrate resistivity, and this is why we are getting the deflection to the right. Okay, and at 7,000 we have no deflection whatsoever. If we have no deflection whatsoever, it could be that this is our base shale line, it could be that it's just a shale, or it could be that there is a sandstone, but the resistivity of the two fluids, formation water and mud filter, are the same. So in that case, we see no deflection whatsoever. So, for example, in this other case, we see the galvanometer, the electrodes, we see 2 shells, and the permanent formation, we see a deflection to the left, and this will be our sandstone baseline and our shell baseline, right? And there is a deflection. So this SP curve is very sensitive to fluids and permeability. So even a small deflection, in the curve is indicating permeability. We don't know quantitatively how much permeability it is, but we can have an idea of that we are changing lithology there. All of this happens as long as there is differences in salinity. If the 2 fluids in contact have the same salinity, there's not going to be ion exchange. There's not going to be fluid flow, current flow. There's not going to be the creation of kinetic and electrochemical spontaneous potential, right? So we do need to have those differences in concentration of the fluids to see the deflections. Okay, and What else can we say? Okay, this is an important thing. The sand line is not going to be the same for all the well because you have differences in salinity when you change the depth. So if you are changing your fluids, if the formation water is changing salinity with depth, your baselines are going to move. But that doesn't mean that your rock is more or less permeable, or I mean, not necessarily that, but it can be just changes in salinity, right? So you have to uh, say this is why correlation is difficult, because if you want to compare two different wells, right, you need to make sure that all those wells that you are correlating have the same mud filtrate and the same water formation or similar. Because if you have different mud filtrate and different formation waters, then that is going to change the deflections and is going to make your interpretation more difficult. Okay. Let's see what else we have here. There is a lot of math involved in this. If you want to calculate water resistivity from SP curves, there's so many methods and many formulas, and even you can try to calculate volume of shell with this, but it is not recommended. For volume of shell, it's more recommended gamma ray or density, sonic density, and nutrient density, and nutrient porosity. Okay, so basically what the SP log help us detect permeable beds, because as we said before, even small deflections to the right or to the left, depending on the salinity and the fluids, is an indication of permeability. Okay. It helps us also with all these formulas, all this math, and all these plots, graphs that we have down there in this document. It helps us determine the water resistivity of water if we don't have access to formation water to test the salinity. And also is an indicator of the shaliness of the formation and correlation. But as we said before, correlation, we have to make sure that we are comparing apples with apples, right? Because we shouldn't compare wells that have different formation waters and different mud filtrate. Okay. Again, here we're explaining the same, like the difference between the SP, the shale baseline, and the sand baseline is the SSP value. And here we can see how the SP log is changing and is deflecting to the left or to the right. This is our shale baseline. And depending on the type of fluid, and also actually, for example, here we can have a shale, and we can also have a different lithology here, right here. But if the salinity is not changing, or if they have the same permeability, if both are impermeable, it doesn't matter that they have different lithologies. The SP curve will not recognize that because it's not sensitive to that. Okay, so we have those are the two scenarios where the curve is going to look flat in impermeable, not permeability variation, and not salinity variation, or no salinity difference between the two fluids that have been in contact. Okay, and also here, if we have fresh water, then the reflection will be the moving of the ions, and the direction of the flow will be in opposite directions, and then the current will generate will be a positive potential instead of a negative one. Okay. Okay. What else can we say about this? Is the same thing that we were discussing before, that the SP curve has two possible sources and two possible contributions. So here what we can see in this plot is that, okay, we have our shale, our permeable sandstone, and another shale, And we can see that, as they say here, we have a mud-K potential, EMC, and we have a diffusion potential, ED. And they are assuming that at point A in the borehole has some unknown potential relative to the surface E sub 0. But what's going on here is that current is moving from A to B, from B to C. And by moving from these points, they are creating a current, and they're creating a voltage or a potential, spontaneous potential. So here this is the line. This is the line for our sandstone, and here we can see that this potential of sandstone is the sum of the mud-K potential. It is the plus diffusion potential plus the shale membrane potential. Okay, so those are the components of the curve, and that is the explanation of why we have this huge deflection to the left, and that is again indicating to us that there is a permeability change or lithology change. So this is basically what is going on here. Also, here we can see that chlorine ions, they move faster than sodium. But for example, when they get in contact with the shell, there's a membrane effect here, and there's some repulsive behavior. I don't know how to say that. It's hard for the ions to pass this shell barrier, and there's some of them are excluded. And okay, and this is the membrane potential effect. So, but that's basically what's happening with this spontaneous potential lack. You have these currents and this movement of fluids and ions generating potential, and that's what the tool is measuring. And when it comes to interpretation, as we said before, we need to let's see some examples of this. Okay, we have resistivity and we have SP log. We haven't covered resistivity yet, but let's focus on the SP deflections. So you can see that maybe you have to calibrate and say where is our shale. So for example, here we can see that the white spots are the shale, so that would be our shale baseline. But here we can see that here we're deflecting from the base shale line because the log is indicating some permeability. So, but this is for a salt. Okay, so now this, if we didn't know that it was salt, we would confuse this with maybe with a sandstone or something like that, because it's an indication, but it's not. You have to know your reservoir, right, as well. You have to have context for this. But up here in the Ogallala Formation, we can see that there's deflection to the left from the base shale line, and that's sandstone. But this one is another thing. But it's looking, the deflection is looking a little different. But let's see more examples of this. For example, in silt, there's a small deflection. Here another small deflection. This is a sandstone. So yeah, we can see the deflection. So basically, it's gonna help us. It's gonna help us determine our shale. It's gonna give us an indication of the permeable, our permeability, and again the same graph that we were seeing everywhere, that there is some shale baseline drifting with depth, and that happens because of variation in salinity. And again, this is for wastewater, for salt water, permeable, brackish water. This is the same example that we were looking at before. And here we see shale A, shale sandstone B. Okay, so there's also some drifting here because the shale line is different from shale A to shale C, and we see that there is more deflection for sandstone B than for sandstone D. Sandstone F has way more deflection, and this shale baseline, there is drifting. So there's a lot of changes in fluids here. And in this other example, we see the SP for our sandstone, for our shale. So there is a sandstone here. We have a couple, and actually these are resistivities. The resistivity. Oh, wow! There's a lot of difference between the deep resistivity of the virgin zone and the invaded zone. And here we see that there is more deflection for our green sandstone, less deflection for the Cook formation, and Eldorado formation has. There is something changing here, because like you can see the differences in this for the same sandstone. So there's something going on with the fluids here. So in summary, the SP curves or spontaneous potential curve log, it has an application for delineating shale formations from shale-free high permeability sandstone or carbonate formations. It helps us defining the bed boundaries between such formations within a locked section. The slope of the SP curve is proportional to the intensity of the SP currents in the borehole depth. That's what can cause drifting. Because the current intensity is highest at the boundaries of the permeable formation, the slope of the SP curve is at a maximum, and an inflection point occurs at these boundaries. The SP can also be used to determine the formation water resistivity and for well-to-well correlations. It has limitations for determining the more subtle lithological boundaries and changes, which are better resolved by higher vertical resolution dBeater and borehole imaging logs. I think the resolution of this SP log, let's say, is from 6 to 10 feet or something like that. Don't quote me on this. But yeah, the dBeater or borehole imaging, they have high resolution. They can pick up way more thin layers and stuff like that. So care should be taken to account for any drift with depth in the SP shale baseline and changes in the formation water salinities with depth in the well, as well as the effects of different mud filter invasion. Wellbore diameter changes, wellbore diameter changes and other anomalies. Compensation should be made for the suppressing effects of hydrocarbons on the SP response and in low permeability formations other than shale, such as tight sandstone and tight carbonates. As a consequence, deriving the formational lithology from an SP curve alone is not straightforward and requires a good understanding of and corrections for the various elements of the borehole environment for an effective interpretation. So this is why we gotta be using SP curve in conjunction or in combination with other logs that they're going to secure interpretation, so that we don't confuse things, because we have to make a lot of corrections. Anyway, I hope that this was helpful, and in the next video we'll be picking another log and we will be covering those topics, tools.